Hello everyone, my name is Anam Tahir and today I will be presenting our paper with the title Learning MeanField Control for Delayed Information Load Balancing in Large Queuing Systems. The other authors with me are Kai and Professor Dr. Heinz Koeppl, and we are members of the Self-Organizing Systems Lab at the Technische Universität Darmstadt. So I would like to start this talk by giving a brief introduction to what mean field control actually is. So if you have a system which has a large number of operative agents and that these agents are interchangeable and indistinguishable, then this system using mean field control can be converted into a system where each agent is interacting only through the distribution of all agents. This distribution is known as the mean field of the agents. This formulation using mean field control thus becomes independent of the number of agents in the system and can be used to find scalable solutions. It has already been shown in previous works that the mean field learned solutions are approximately optimal in sufficiently large systems. Due to this, we have also used mean field control to solve a large load balancing system. The load balancing model that we have used in our work is consisting of n clients or agents and m homogeneous servers, where each server has its own finite queue with the maximum buffer capacity of B, which means that at any time point t, a queue cannot hold more than B jobs in it. The jobs are taken from the queue by the server one at a time in a first order manner and are processed at an exponential service rate. The jobs arriving have also an inter-arrival time distributed according to exponential distribution, and all the jobs that arrive the system in a certain interval are randomly distributed amongst the n agents. Now, upon receiving some jobs, an agent then needs to allocate them to the queues so that the servers can process them. For this, every agent samples D queues out of these M queues where D is much less than M and wants to know the state of these D queues. Once the state is known, the jobs are then allocated to these D queues according to some policy pi that is being followed by the agents. Now, due to the network delays, information of the queue states cannot reach the agents instantaneously. To cater this delayed information, we have introduced a synchronization delay delta t into our system. And we assume that the state of the sample D queues is sent to the agents every delta t, and then this state is maintained for the entire delta t duration. So delta t is also the decision epoch for our discrete system. The main research focus for this work was to analyze a load balancing in a large finite queuing system while considering the different synchronization delays. And we are particularly interested in learning a policy for the intermediate values of the synchronization delays. Because it has already been shown before that if the delay is very less, then join the shortest queue is a good policy for the homogeneous servers. And if the delay is very large, then random policy is optimal. So we want to look at what would be a good policy for the intermediate values of delta t. And then we also want to show that the mean field control formulation can help us achieve scalable solutions when the system size is large. So what we do is that we model our n-agent MQ finite model as a multi-agent Markov decision process with n cooperative agents. The queue state space is finite up to the buffer capacity B. The agent state space is consisting of the M queues out of which D are sampled at every time step. And the action space of the agent consists of the D queues that it has access to. Now, at any discrete time t for this NM system, the agent has a state X and an action U, and the QJ has a state Z. While the arrival rate to this system is independently Markov modulated by using a transition kernel P. For simplicity, we have omitted the NM superscripts from the notations, and they will be added later in the talk. Now I would like to explain the dynamics of the queue for this finite NM system. So for every qj, the initial state at time t is equals to 0 is sampled from an initial q state distribution nu naught, which is predefined. The jobs that depart from the queue depart at an exponential rate of alpha, which is the rate of service of the servers. And the jobs arrive at any qj according to rate lambda tj, which depends on the total arrivals to the system, the total arrival rate of the system, and then how many agents have access to qj and how many agents then end up sending their jobs to qj. For example, if you see in this figure, the arrival rate of Q2 will depend on how many agents have access to Q2, which is S1, S2, and S3 in this example, and then how many agents actually sent to Q2. So the arrival rate at this time instant for Q2 will only depend on S1 and S3. The next Q state is obtained by simulating a continuous time Markov chain for the delta t time units, where an increment or a decrement is done based on the arrivals and departures of which depend on these rates given above. While the empirical Q state distribution to analyze the states of the queues can be given by H. Now, for the dynamics of the agents for this finite system, every agent has its own state, xti, which is the d sampled queues out of the m queues. These queues are randomly sampled. And then the state of the queues for agent I has access to can also be found by using the states that of the queues itself and the d queues it has access to. The action of agent I is sampled from a shared policy pi, which depends on the empirical Q state distribution, the state of the queues agent I has access to, and the arrival rate to the system. While the empirical agent state action distribution can then be given by G. So since we have finite queues, any queue, if it is full and a job arrives to it, it is dropped. And these drops are then counted in the average number of dropped packets in the entire system. And then our goal for this learning is to minimize the overall job drops in the system. For this, we have designed this infinite horizon objective J, which we need to maximize in order to minimize the drops in the system. So the notations or the variables that we have seen up till now are the Q state distribution, which is the empirical Q state distribution over the Q states, the state of the agent, which is the D sample Qs out of the M for each agent I, the decision rule, which depends on the empirical Q state distribution, the state of agents, and the arrival rate, and then the state action distribution, which depends on which state was the agent in and what action it took at that time, and the arrival rate itself. Now we will bring back the NM notations into the variables to make them more consistent with how they are in the paper. Now for the MeanField control formulation, what we assume, or our main assumption, is that both the n number of agents and m the number of queues go to infinity, which means that we cannot deal with individual qj or individual agent I anymore. We deal with their the distribution over their states only. And how we do this is, now we have for the q state distribution and a distribution nu t over the states of the qz. The agent state distribution nu t can be found by using this agent the q state distribution for the DQs that every agent has access to. So all the possible states that the agent can have are calculated using this. Then the decision rule or the control law depends now on the Q state distribution, the agent state distribution, and the arrival rate. The state action distribution can also be found similarly, and the arrival rate. So once we have this limiting MeanField control formulation, this limiting system is evolved using the exact discretization of the Kolmogorov forward equations. And the details of it can be found in our paper by the interested readers. Now, what we have done so far is that we have converted a large multi-agent NM system, which was modeled as a multi-agent Markov decision process, to a single agent mean field control Markov decision process. Our discount objective remains the same, except now we look at the total drops in the mean field control MDP system. And we want to now learn an upper policy pi tilde, which maximizes this reward. And then how we do this is we use proximal policy optimization algorithm from reinforcement learning to learn this policy pi tilde. Once we have this upper level policy, then the samples, then the actions for the finite NM system can be sampled from it. And how we can simulate our mean field control policy to a finite NM system is given in this algorithm. So what we need for this algorithm is as input the system parameters which are given in the paper and the Markovian upper level policy that we have learned using PPO. We then initialize the arrival rate and the Q states of all the MQs. Then for every epoch, what we do is we first compute the empirical distribution H. We then sample a decision rule depending on this H and the arrival rate from this upper level policy pi tilde. Then for every agent N, we sample an agent state out of these MQs, which is then we compute the state of these MQs, DQs, sorry. And then after we have the state, then we can use this decision rule to sample the action for agent I depending on what state its Q was in. Once we have the actions for all N agents, we can take these actions on the Qs and can then simulate the next Q state using continuous time Markov chain and count the number of dropped packets in this epoch. Then we sample a new arrival rate and go on until the end of episodes. At the end, we get the number of dropped packets in the system over the entire episodes. The code for this algorithm is available publicly on GitHub, and the link for this is available in our paper. So now for the experimental setup, what we have used is d is equals to 2 for all our experiments, which means that all agents sample 2 Qs at every decision epoch. The algorithms that we have compared our mean field control policy with are JSQ2 and random. In JSQ2, you sample 2 Qs and then join the one which is shorter or has less jobs in it. In the random policy, you sample 2 Qs and join any of them randomly. So for every delta t, we have trained a separate mean field policy and then applied it to the finite NN system using the algorithm shown before. And for an easy comparison between different delta t's, we have set an episode length of or equal episode length of 500, and we see how many drops happen for every delta t in 500 seconds. So we run every system for the same amount of time, which is 500 seconds. So the first result that I would like to show you guys is of the application of our mean field policy on our finite system. And this shows the performance of the final learned mean field policy over a wide range of delta t's. So on this top of the subfigures, we have the delta t's that are used, ranging from 1 to 10. On the x-axis, we have the number of Qs, and the number of agents is m squared. On the y-axis, we have the average dropped packets. The red dotted line is the performance achieved in the mean field control setup. And as we can see that as the system size increases, which means that as n and m both increase, the overall achievable performance can be reached. So these results verify our theoretical proof that the mean field system performance, which is the red dotted line, can be achieved with arbitrary precision when the system size gets large enough. Next, we show the experiments for large systems and compare it to the two other algorithms, JSQ and random. For this, as on the x-axis, we have the different delta t's ranging from 1 to 10. On the y-axis, we have the total dropped packets. And on the top of the subfigures, we have the number of queues that are used, while the number of agents is m squared. So here we can see that for all delta t's, our MeanField policy outperforms the random policy, while our MeanField policy has comparable or better performance than JSQ. And it can be seen that as delta t keeps increasing, that MeanField and the random policy are likely to perform equally good as long as the system size is large enough. Next, what we have done is an ablation study where we do not assume that the number of agents is much larger than the number of queues. And there we can also still see that our MeanField policy obtains better performance than both JSQ and random. This further gives confidence that we can apply this policy to any system, even though it violates our theoretical assumptions. So, to summarize, the main contributions from our work are that we consider a model with synchronous communication delay and formulated as a MeanField control problem. We theoretically prove that the limiting system performance is reached with arbitrary precision as long as the system size is large enough. We find that as the synchronization delay increases to an intermediate value, the shortest queue and the random assignments are suboptimal, and there is a need for a learned policy which can outperform both of them. And our claims are supported both theoretically and experimentally, and we are able to give a good solution for large-scale load balancing system with many clients and servers. In future, we would like to consider a few directions for this work. We would first like to compare it to the other state-of-the-art algorithms. Then we would like to consider the cases where the buffer size is large enough or is finite, and also the servers are heterogeneous. We would also like to analyze when the system, when the inter-arrival and service times are non-exponential and the system does not remain Markov anymore. And then we also would be interested in seeing if there is partial observability of the queue states by the agent, so delay and partial. And then an implementation on the real world system would be also very interesting. So I thank you for your attention.